The Webb look is so far out that discovering light has been traveling for north of 13 billion years. At this point, the universe has been growing, and subsequently, the light has been reaching out for the most far-off universes. We're recalling in time almost to the enormous detonation. The tremendousness of the universe could appear to be immense, yet every single bit of it started from what we imply as the peculiarity. At this point, this is the way we could decipher the huge explosion hypothesis. In any case, the James Webb Space Telescope, JWST, has revealed significant secrets about the birth and development of the universe, leaving us confused. Renowned physicist Brian Cox has declared that the important discoveries made by the JWST could really reshape how we might interpret the universe in general. Go along with us as we plunge into these new, great revelations that promise to change our consciousness. The James Webb Space Telescope, named after the recognized NASA chief James E. Webb, stands as a marvel in current cosmic research. This telescope represents a colossal technological leap forward from its predecessor, the Hubble Space Telescope. It resulted from a cooperative effort between NASA, the European Space Agency, and the Canadian Space Agency. The JWST outperforms the capabilities of its ancestor. It uses cutting-edge technology and a design optimized for focusing on the universe in surprising detail. Unlike the Hubble, the JWST delivers clear and sharp images of distant brilliant bodies, working primarily in the infrared range. This fascinating feature allows it to penetrate galactic dust and capture celestial objects that were previously hidden from our view. With its massive 6.5-meter primary mirror, made of 18 hexagonal segments, the JWST dwarfs the Hubble's reflector size. Positioned roughly 1.5 million kilometers away from Earth at the second Lagrange point, L2, it orbits the Sun in harmony with Earth, ensuring a stable and uninterrupted view of the universe. While investigating the faraway corners of the universe involves light years, it also involves a kind of time travel. The JWST utilizes infrared instruments to see celestial objects and events dating back billions of years. The light emitted by these objects, due to the expanding universe, undergoes redshift, moving from the visible range to the infrared frequency, longer wavelengths. Fortunately, the JWST can detect infrared light emitted by distant celestial bodies, enabling scientists to study the birth of stars, research galaxy development, and examine exoplanet atmospheres. Its latest historic discovery involves identifying an incredible mass of galaxies at the edge of the observable universe. This finding challenges the validity of current theories about cosmic origins, prompting a reassessment of fundamental cosmological assumptions. To better understand how we arrived at this point, we should take a short journey through the history of space exploration. Early civilizations like the Greeks and Chinese laid the groundwork for understanding planetary development by observing celestial bodies. Newton's laws in the 17th century provided a theoretical framework for space travel. During the 20th century, Edwin Hubble, an influential astronomer, made groundbreaking discoveries in cosmology and observational astronomy. His observations revealed that distant nebulae were independent galaxies beyond the Milky Way, transforming our understanding of the universe's size and scale. Hubble's law, established by him, showed that galaxies farther away were moving away at higher speeds, providing evidence for the expansion of the universe. The post-World War II era of space exploration marked the beginning of the space race, with the Soviet Union Sputnik in 1957 as the first artificial satellite. Yuri Gagarin's orbital trip in 1961 and the Apollo 11 moon landing in 1969 were pivotal achievements. Fast forward to 1990, when the Hubble Space Telescope was launched, providing unprecedented clarity and stunning insights into the universe. The journey from ancient observations to the technological wonders of the James Webb Space Telescope highlights the continuous advancement of how we interpret the universe. The Hubble Space Telescope, HST, for example, captured the famous Pillars of Creation image in the Eagle Nebula, revealing a star nursery formed by massive columns of gas and dust. Another significant milestone was the Hubble Deep Field, which captured countless galaxies in what appeared to be an empty patch of space. The HST also explored exoplanet atmospheres, pinpointing elements like water and organic molecules in distant worlds, suggesting the possibility of habitable zones beyond our solar system. By observing the nearest supernova, SN 1987A, it shed light on the life cycle of massive stars. These achievements solidified the Hubble's legacy as a foundation of modern cosmology, astounding the world with its incredible discoveries. Its successor, the James Webb Space Telescope, was launched to build upon the technological advancements and lessons learned. Today, the widely accepted theory of the universe's origin is explained by the Big Bang theory. About 13.8 billion years ago, the universe began as an incredibly hot and dense singularity, rapidly expanding and leading to the formation of matter, energy, and fundamental forces. As the universe expanded, it cooled, resulting in the formation of atoms, stars, galaxies, and the diverse structures we observe today. The Big Bang theory also explains cosmic microwave background radiation, light element abundance, and the large-scale structure of the universe. Despite its wide acceptance now, the theory faced skepticism and challenges in its early days. Alternative models like the steady-state theory proposed a universe without a specific beginning. Concerns about evidence supporting the initial singularity and observed inconsistencies also emerged. Many of these objections were addressed over time, particularly with the detection of cosmic microwave background radiation in 1965, aligning with Big Bang predictions. Space missions like COBE and WMAP, alongside technological advancements, further supported the theory. Precise measurements of cosmic microwave background radiation matched remarkably well with theoretical predictions. Enter the James Webb Space Telescope. Equipped with advanced infrared instruments that can peer through cosmic dust, the JWST primarily operates in the infrared range. It captures the oldest light in the universe and observes objects formed shortly after the Big Bang. Its infrared capabilities allow it to study star-forming regions, celestial nurseries, and the birth of stars, phenomena hidden from optical telescopes. Infrared light, with longer wavelengths compared to visible light, penetrates interstellar dust, overcoming one of the Hubble Space Telescope's limitations. The JWST can observe cooler objects emitting primarily in infrared, making it ideal for studying phenomena like exoplanets, brown dwarfs, and distant galaxies. As celestial bodies move away, their emitted light waves get stretched, causing a redshift toward longer wavelengths. The JWST's infrared capabilities detect these redshifted signals, capturing light from the early universe and providing insights into its formation and evolution. Energetic events like black hole mergers or new starbirths primarily emit in the infrared range, further expanding the JWST's investigative abilities. The telescope can explore phenomena that would otherwise be hidden or invisible. Complete radiation. This ability allows it to peer further into space and dig deeper into astronomical history, revealing hidden astronomical wonders and providing a more comprehensive view of the universe's development. The JWST serves as our window into the earlier phases of cosmic evolution. Recently, it revealed something so astounding that it might prompt a reconsideration of the entire cosmological model of the universe. We've discovered enormous masses of galaxies at the very edge of the observable universe. These ancient galaxies existed just a few 100 million years after the Big Bang, during the cosmic dawn. The puzzling part is that we're unsure about how such enormous structures formed so early in the universe's history. This discovery might lead us to reconsider our understanding of the formation and evolution of galaxies in the early universe. Studying early galaxies is crucial for unraveling the mysteries of cosmic origins. The JWST can gain insights into how galaxies, stars, and planetary systems arose and evolved over billions of years. These observations also contribute to broader questions about the fundamental nature of the universe, including its composition, structure, and the forces governing its evolution. While the Hubble Space Telescope was groundbreaking for its time, it had limitations in observing the early universe. Its main limitation was its inability to effectively penetrate cosmic dust and detect the infrared light emitted by ancient galaxies. Older telescopes relied on visible and ultraviolet light observations, making it challenging to explore the early universe, where these wavelengths are absorbed or distorted by interstellar dust and gas. The James Webb Space Telescope represents a significant leap forward in observing galaxies from the universe's early stages. Unlike its predecessors, the JWST can observe celestial objects that formed within a few 100 million years after the Big Bang. Using its infrared sensitivity and advanced imaging capabilities, the JWST has uncovered an abundance of ancient galaxies, offering remarkable clarity and detail in understanding the universe's evolutionary history. Preliminary results from JWST observations have stirred waves in established cosmological models. The detailed data challenges several aspects of prevailing theories, prompting cosmologists to reconsider fundamental principles governing how we understand cosmic evolution and structure. Discrepancies between observed data and theoretical predictions have sparked intense debates within the scientific community. JWST observations have revealed a larger number of galaxies in the early universe than anticipated by existing models, suggesting a more complex and rapid evolution process. Some observed early galaxies appear more developed than expected, challenging conventional models predicting slower development. The discovery of an unfathomable mass of galaxies challenges the assumed distribution and arrangement of large structures, revealing a more intricate and denser cosmic web than previously thought. These observations raise fascinating questions and avenues for further exploration. The existence of large structures challenges early models of cosmic structure formation, prompting researchers to refine models for a better explanation. Understanding how such vast structures gathered rapidly after the Big Bang presents a puzzle that requires an explanation that doesn't violate fundamental principles of cosmology. Significant disparities in the conditions of the early universe compared to predictions based on existing models have also been revealed. These differences could suggest previously unknown physical processes, unexpected conditions, or unidentified cosmic phenomena. In simple terms, these variations have prompted scientists to rethink and improve our models of the universe. Currently, all we can do is say that further exploration is required to incorporate these surprising observations into a more comprehensive understanding of the universe. Initial observations often provide exciting glimpses into the universe, but in-depth investigation sometimes reveals differences. For example, early observations may show specific properties or arrangements within distant galaxies that, upon closer examination, reveal fluctuations in their composition, structure, or evolutionary pathways. In conclusion, enormous phenomena are incredibly complex and require careful investigation for us to accurately understand their true nature. Spectroscopy, a method that helps unravel the properties and history of celestial objects, is an example. It involves analyzing the light emitted or absorbed by astronomical objects. By examining the properties of the light, spectroscopy provides detailed information about the chemical composition, temperature, density, and movement of celestial bodies. This analysis helps us understand the origins, development, and contributions of celestial bodies to the cosmic tapestry. The JWST has uncovered numerous cases where initial observations differed from later investigations. For instance, initial observations of distant galaxies suggested a simple structure primarily dominated by lighter elements like hydrogen and helium, in line with theoretical expectations. However, spectroscopic analysis using the JWST showed fascinating variations in elemental signatures, identifying heavier elements or compounds previously undetected or misunderstood in the early universe. This challenges conventional ideas about the early universe's chemical composition and the mechanisms responsible for their development and dispersion across vast distances. Similarly, initial assumptions about galaxies in the early universe were based on preliminary observations suggesting a relatively uniform pattern of development and organization. However, more detailed investigations by the JWST revealed a much more diverse and complex array of chemical compositions within these galaxies. The revelations from the James Webb Space Telescope, JWST, continue to push the boundaries of our understanding of the cosmos. As it peers into the farthest reaches of space, the JWST is shedding light on previously hidden aspects of the universe's early history. With its cutting-edge infrared capabilities, the telescope allows scientists to observe the universe as it was just a few 100 million years after the Big Bang. These findings not only challenge previous models of galaxy formation but also provide tantalizing clues about the physics of the early universe that we are only beginning to understand. For instance, The JWST's ability to detect faint signals from the first galaxies has opened up an entirely new field of exploration. These early galaxies are often much more complex than previously thought, exhibiting a level of structure and maturity that defies current theories. The question arises: how did such early galaxies form and evolve so quickly? One possibility is that they underwent rapid bursts of star formation driven by interactions with nearby galaxies or gas-rich environments. Alternatively, the JWST findings could point to previously unknown physical processes at play, which may require a significant revision of the current models of cosmic evolution. Moreover, the JWST's exploration of exoplanets has opened up exciting new avenues in the search for extraterrestrial life. The telescope's ability to analyze exoplanet atmospheres in unprecedented detail could lead to the discovery of biosignatures or conditions that are conducive to life. By observing chemical signatures in distant atmospheres, scientists may eventually identify planets that share similarities with Earth, providing new targets for astrobiological research. The sheer scale of the JWST observations also challenges our traditional understanding of the universe's structure. For centuries, we've thought of the universe in terms of galaxies and clusters of galaxies. But the JWST data hints at a far more intricate web of cosmic structures. This complexity could hold the key to understanding dark matter, dark energy, and the large-scale structure of the universe, which remain some of the most enigmatic aspects of modern cosmology. As we continue to analyze the data sent back by the JWST, the discoveries will likely redefine our place in the universe and alter the course of astronomical research for decades to come. The potential to uncover new laws of physics, along with a deeper understanding of the universe's early conditions, holds profound implications not just for astronomy but for the future of humanity's quest for knowledge.